Hello AP Statistics, this is Mr. Moon, and today I'm going to be talking about random variables. This is our first lesson in Chapter 6, and this is Section 6.1, which is all about discrete and continuous random variables. This builds off the work we've been doing in Chapter 5 with probability, so you may want to think back to those concepts as we begin today. Okay, after this section, you should be able to apply the concept of discrete random variables to a variety of statistical settings, calculate and interpret the mean, or what we call expected value of a discrete random variable. We'll be able to calculate and interpret the standard deviation and variance of a discrete random variable, and we'll be able to describe continuous random variables. Okay. And by the way, we might not get to all those objectives in this video, but we will in class when we catch up. So first of all, we've seen last time that a probability model, this was in the last chapter, describes the possible outcomes of a chance process and the likelihood that these outcomes will occur. Think back to when we drew up our table with all the various scores you can get on a pair of dice and how likely each of those scores was to happen. So a numerical variable that describes the outcomes of a chance process, this is called a random variable. So think again to our dice rolls, to our coin flips, right? The probability model for a random variable is its probability distribution. So a random variable again takes numerical values that describe the outcomes of some chance process. The probability distribution of a random variable gives its possible values and their probabilities. So let's consider tossing a fair coin 3 times. Define x here as the number of heads obtained. So there's our random variable. Now, notice, we can either get 0 heads, 1 heads, 2 heads, or 3 heads. So those are our different possibilities, and we're going to have a different probability of each. So the only way to get 0 heads is to flip tails, tails, tails. There are 3 ways to get 1 heads. You can get heads, tails, 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 heads, tails, or tails, tails, heads. With 2 heads, there are again 3 ways. You can get heads, heads, tails, heads, tails, heads, tails, heads, heads. Finally, there's only 1 way to get 3 heads. That's heads, heads, heads. So if we draw up this probability model, what we're going to see is that there are 4 possible values here. We have 0, 1, 2, and 3. Each of those has a different probability. There's 1 way out of 8 total to get 0 heads, 3 ways out of 8 total to get 1 head, there's 3 ways out of 8 total to get 2 heads, and there's 1 way out of 8 total to get 3 heads. If we graph that, it'll look something like this. There's a 1/8 chance of getting a 0, there's a 3/8 chance of getting a 1, there's a 3/8 chance of getting a 2, and again a 1/8 chance of getting a 3. Notice just by the way that this is beginning to look sort of like our normal curve, and we'll kind of see why that is maybe a little later down the road. There are 2 main types of discrete random variables. So first you have your discrete random variables, and this would be one where you can list all possible outcomes for a random variable and assign probabilities to each one. That was our number of heads in the last example was a discrete random variable because the outcomes were 0, 1, 2, and 3. There were not outcomes in between those. There were not more than that. And we were able to find the probability of each one. So a discrete random variable x takes a fixed set of possible values with gaps between. So again, there's not other possibilities between 2 values. The probability distribution of a discrete random variable x lists the values, which we're going to call each one of them xi, and their probabilities pi. So in other words, value x1, x2, and x3, which would be like the 0, 1, 2, and 3 in the last example, will have probabilities p1, p2, p3. So this would be like the 1/8, 3/8, 3/8, 1/8 in the last example. Okay. Those probabilities, PI, all of them, must satisfy two requirements. I bet you guys know what these are going to be. First off, every probability, PI, must be a number between 0 and 1. So that's from the last chapter, right? Probabilities are between 0 and 1. Second, the sum of the probabilities is 1. Again, you guys know that from last chapter. If I flip 3 coins, one of the 4 outcomes has to happen, right? Either 0, 1, 2, or 3 heads. Okay? Finally, to find the probability of any event, add the probabilities PI of the particular values XI that make up the event. In other words, if we wanted to know the probability of getting 2 heads or greater, we'd add the 3/8 probability for 2 heads and the 1/8 probability for 3 heads to get 4/8 or 1/2 total. We're going to look at that in a later example. Bounce, bounce, bounce. Okay, so baby's health at birth. We don't have the example on page 343. So, okay, here's what we're looking at. So these are our values for what's called APGAR scores. And what we need to do is first just show that the probability distribution for X is legitimate. So I'm scanning across this table right now. I am seeing that each of these probabilities is between 0 and 1. That's good. Now what I want you guys to do is go into this table, add up all the probabilities, and confirm that this is a legitimate probability distribution because all the probabilities should add up to 1. So if they add up to 1, this is legit. If they do not all add to 1, this is not a legitimate probability model. Okay, skip the histogram set. You could do that. It would look a whole lot like that histogram we made for the coin flips earlier, but there may be space for that on your notes. Don't worry about that too much for now. What I want to focus on is C. APGAR scores of 7 or higher indicate a healthy baby. So what is P, X is greater than 7? So first of all, I'm going to fill in the answer from earlier. All probabilities are between 0 and 1, and they add up to 1. This is a legit probability distribution. B, we're going to see a histogram that looks something like this. Notice we're graphing probabilities on the Y, APGAR scores, which is our random variable, on the X. Okay. Finally, let's look at what P of X greater than or equal to 7 is. To do this, we're going to need to add the probabilities from 7, 8, 9, and 10. Okay? So again, we're adding those 4 up, and we come up with a 0.908 as our probability. So that's about a 91% chance of randomly choosing a healthy baby, meaning an APGAR score of 7 or higher. Okay? So again, when the probabilities encompass kind of multiple outcomes, when the event encompasses multiple outcomes, just add together the probabilities of each of those outcomes. Okay, so that's all we did there, added together those probabilities. Okay, so let's take a peek at this example here. We have North Carolina State University posted the grade distributions for its courses online. Students in Stat 101, hey, stats, in a recent semester received 26% A's, 42% B's, 20% C's, 10% D's, and 2% F's. So if we choose a Stat 101 student at random, the student's grade on a 4-point scale with A equals 4, B equals 3, and so on, is a discrete random variable X. I guess you can't get a 3.7 at NC State. Interesting. And here's our probability distribution. So what we're seeing here is that F happens at a 2% rate, D happens at a 10% rate, C happens at a 20% rate, 3 happens at a 42% rate, and A happens at a 26% rate. Now I'm adding these together. Let's see. A's and B's, that's 68%, plus the C's, we move up to 88%, plus the D's, we move up to 98%, plus the F's, that gives us 100%. So this probability model looks legit because all the probabilities are between 0 and 1, and they add up to a total of 100% or 1. Okay? Now, let's say in words what the meaning of P of X is greater than or equal to 3 is. So this means that a student has at least a B, which we could also phrase as the student has a B or an A. And the probability of this is going to be 0.42 plus 0.26, which again is going to be 0.68. Now we need to look at the student got a grade worse than C, C's a 2.0, in terms of values of the random variable X. So this would be our 0 and our 1, okay? So we're looking for P of X is less than 2. P of X is less than 2, and that would be the 0.02 for F plus the 0.1 for D. So this is going to give a total probability of 0.12. So P of X less than 2 would be 0.12 or 12%. Finally, if you'd like, you can sketch a graph, which should be a histogram of the probability distribution, and describe what you see. What we probably are going to see here, just looking at those numbers, is a fairly significant left skew. Not a whole lot of students are going to get Fs. Okay. So when analyzing discrete random variables, we are going to use the same strategies we use with quantitative data in our histograms. So check your socks. Describe the shape, center, and spread, and identify any outliers. Now, the mean of any discrete random variable, which we said was the expected outcome, is that what I said earlier? Expected value, excuse me. That's going to be the average of the possible outcomes, but it's a weighted average weighted by the probability. So, again, suppose that X is this discrete random variable whose probability has those values X1, X2, X3, and the probabilities P1, P2, P3. So again, that table that we've seen before. To find the mean, or the expected value of X, what you want to do is multiply each possible value by its probability, then add all the products. It's going to look a lot like this. So mu of X, which is also called E of X, or expected value of X, is going to be X1 times P1 plus X2 times P2 plus X3 times P3 plus and so on. You can also summarize it with that sigma notation, sigma or sum of Xi plus Pi, and just run that through all the X's. Okay. Looking back at APGAR scores, what we want to do here is compute the mean of the random variable X. In this case, X is an APGAR score, and we want to interpret that in context. So remember, here's our formula. The mean, or the expected value, is going to be the sum of the X's times the P's. So what we do here, and this is just to get you started, is we multiply 0 by 0.001. Plus 1 times 0.006, plus 2 times 0.007. Sorry, there's a stray parentheses in there. We add all of them up until 10 times 0.053. So you want to do the ones for 3, 4, 5, 6, 7, 8, and 9 as well. When you add those up, you get 8.128, which means that the mean APGAR score of a randomly selected newborn is 8.128. And this is going to be the long-term average APGAR score of many, many randomly chosen babies. Remember that law of large numbers. It will only approach this mean as we take many, many trials, right? Note here, the expected value does not need to be a possible value of X. It also does not need to be an integer. In this case, it is not. This is a long-term average over many repetitions, right? No baby is going to have an APGAR score of 8.128 because it's always an integer. But the average over many, many repetitions is an 8.128. That's the expected value. I'll leave the comic up for a second. I think some people find this boring. I actually really like this model because it lets you pretty quickly predict what's going to happen if you know the probabilities of a bunch of different events. Okay. Good Lord. Okay, so here's your exit ticket, and I just want you guys to take a look at this one. So in 2010, there were 1,319 games played in the NHL regular season. Imagine selecting one of these games at random and then randomly selecting one of the two teams that played in the game. Define X as the number of goals scored by a randomly selected team in a randomly selected game. The table below gives the probability distribution of X. So we got 0 with its probability, 1 with its probability, 2 with its probability, and so on. First thing I want you guys to do, show that the probability distribution for X is legitimate. Second, calculate the expected value of this discrete random variable X, which would be number of goals scored. So calculate the expected number of goals scored per team per game. Finally, what is the probability that the number of goals scored by a randomly selected team in a randomly selected game, so that's our X, is at least 6. So this is actually written wrong. It should be P of X is greater than or equal to 6. So we are looking at the columns 6, 7, 8, and 9. Okay? Work on that. Gentlemen, you will have a Google form quiz just quickly on this lesson posted to work on over the weekend. Okay? When you come back, we will start work on 6.2, where I believe we'll start to see continuous random variables, which are a whole new ball game in some ways, but also you've kind of done work on this before with norm CDF, which is one way you've already explored continuous random variables. We are going to introduce the binomial distribution and the geometric distribution, but guess what? There's a binom CDF and there's a geom CDF. So you'll be right at home. This is Mr. Moon. I'm going to sign off. Good luck this weekend. See you next week.